Welcome. Today we're diving straight into a profound frontier in both physics and engineering. We're talking about CSDL v1.0, the Configurational Computing System Design Language. But here's the thing. We aren't just looking at this as your standard control language. We're actually anchoring it in one of the most rigorously verified frameworks we have in physics, which is classical electromagnetism. Think of CSDL as a fundamental, hardware-based solver for incredibly complex partial differential equations. The whole idea here is that we are literally stopping the digital simulation of physics. Instead, we're stepping back and allowing physics to actually compute the solutions itself. It's wild.
To really grasp how revolutionary this is, let's just look at how we currently tackle these problems using software like HFSS or CST. You know the drill. Traditional tools rely heavily on FTD, or finite difference time domain methods. What do? They artificially chop up continuous space into these tiny, discrete grids, right? And then they force a computer to grind through literally millions of iterative numerical steps. It's an absolute computational bottleneck, taking anywhere from minutes to hours and burning a ton of energy in the process. Now, CSDL brings a total paradigm shift to the table, and that's physical relaxation. So, instead of that clunky digital grid, we're using continuous time analog circuits. We just let the physical voltages naturally relax into the correct answer. And the best part? It happens in microseconds using a fraction of the energy.
So, how does this analog relaxation actually work? Well, it all boils down to a shared foundational concept that we all know and love, the variational principle, or the principle of least action. We know an electromagnetic field naturally seeks out a state that minimizes its energy functional, which is the integral of the Lagrangian density. If you apply the Euler-Lagrange equations to this action, boom, you directly derive Maxwell's equations. And honestly, this is the core philosophy driving CSDL. We are totally replacing a computer's blind iterative digital search with a totally natural physical relaxation process. Because the hardware inherently minimizes this action functional all on its own, its steady state is, by definition, your exact mathematical answer.
All right, so how do we build this into a practical architecture? CSDL relies on a super strict four-layer abstraction where classical electrodynamics map directly, and I mean directly, onto the hardware. Starting at the physical layer, our state vector, x, perfectly represents the electromagnetic scalar and vector potentials. Then, moving up to the constraint layer, we use what's called the magic hypercube constraint, m. Mathematically, this maps exactly to the Lorentz gauge condition. Finally, in the observation and control layer, our performance index, J, represents electromagnetic energy density. So all that abstract mathematics, it maps flawlessly right onto physical hardware variables.
Let's dive a little deeper into that constraint layer, layer 2, because we run into the absolutely crucial concept of gauge consistency here. To solve Maxwell's equations uniquely, we obviously have to impose a gauge fixing condition, like the Lorentz gauge. Now, in traditional computing, enforcing that across a massive 3D grid requires intense, heavy-duty calculation. But in CSDL, this physical law just maps directly onto that magic hypercube constraint constant. The physical circuit topology is actually designed in such a way that the system simply cannot exist outside of this conserved global sum. The hardware continuously enforces the gauge condition, and there is absolutely zero digital algorithm required to do it.
Moving on, we reach the real engine of the whole setup, Layer 3's observation and control law. As we established earlier, the system naturally wants to minimize energy, which is defined here by Poynting's theorem. Well, in CSDL, our performance index J operates exactly as this state-dependent energy function. Think about it. If you introduce a disturbance, say a new antenna parameter, the physical circuit naturally utilizes gradient descent. It just rapidly dissipates that energy, naturally settling right into the lowest possible energy state that still satisfies the Lorentz gauge constraint. You're watching the hardware natively implement the steepest descent of Maxwell's equations in real time.
Translating all this beautiful math into physical reality brings us to the ABN-QSS V2.0 analog coprocessor. Instead of simulating a chunky 3D grid with millions of individual voxels, this microchip utilizes a physical OTA-C network that's an operational transconductance amplifier and capacitor array. By carefully tuning the coupling matrix, or GM, the voltage distribution across this continuous time analog chip automatically mimics the exact magnetic and electric vector potentials you're trying to study. It can rapidly discover resonance modes of incredibly complex cavities in mere microseconds. The key takeaway here is that the microchip isn't calculating the electromagnetic wave, it is physically becoming the electromagnetic field itself.
This isn't just some abstract theory anymore. We're looking at a validated, entirely new standard for computational electrodynamics. The ABN-QSS team is actively inviting collaboration. So, if you're a researcher working in electromagnetics, accelerator physics, or looking into post-Moore architectures, this framework is absolutely ready for you. By utilizing the CSDL digital twin and the hardware blueprint, you can completely offload that massive burden of field solving from your digital clusters directly onto specialized analog hardware, which will radically reduce your design cycles. I'm going to leave you with this final thought. If the physical universe doesn't need to run billions of lines of code to balance an electromagnetic field, why should your computer? Keep questioning how we compute.